Do an example on electrical flux, and I want to find out what is the electrical flux through a certain open surface. So electrical flux is defined as integral of E dotted into dA. The units of it is Newton per Coulomb times meter squared. So imagine that we have a surface like this, okay, some kind of surface. Could be some kind of weird looking surface, y equals x squared. And imagine this is the xy axis, and there's electrical field emanating from out of this page. Okay? So basically the concept of electrical flux is multiplying that electrical field coming out by the surface area. Okay? So the electrical field, let's say it's some vector like this. 2I hat plus 4j hat plus 8k hat. So what does that mean? In this case, the electrical field is a constant vector. It has a component to the right, up and out. To the right is 2, up is 4, out is 8. Okay? Which component of this electrical field will actually have a flux? Okay? It's only the 8, the out component. The 2 and the 4 basically glide. The 2 is this way, okay? And then the 4 is this way. So the 2 and the 4 basically glide along the surface without causing a net flux. Okay? That's what it means by the dot product. The dot product of this and this with that is 0. The only component that will have a flux is this. The formal way to prove that is to do this. Is to say the flux is going to equal 2I hat plus 4j hat plus 8k hat times the dA vector, which is dA I hat plus if the area vector, well in this case the area vector, since the surface is on the xy plane, the area vector is coming out of the board, so the area vector only has a z component, right? Only coming out of the board. So basically the dA vector is going to be dA k hat. Okay, so the area vector is always perpendicular to the surface itself. So if I take the dot product of the two, what do I get? The ij cancels out, 8 dA, so the flux is going to be integral 8 dA, and notice here the flux is a scalar. When you dot product two vectors, you get a scalar, so it's just a number. So now you're going to have 8 dA, and then the 8, and then dA is equal to y dx. So I can take a little piece of the object, y dx. Okay? So you have like that. And now what are you going to do? Well, you could say y equals to x squared. And let's say I'm going from 0, 0 to 2, 4. Right? So now I'm going to go from 0 to 2. 8x cubed over 3. Right? So 8 is because of the electrical field. X cubed over 3. From 0 to 2. 8/3 times 2 cubed is 8. So 64 over 3. Which is 20, 21 and 1/3, 3, 3, 3, 3, repeating threes, and that's in units of Newton per Coulomb meter squared. So you can see example there of the electrical flux. This is for if the electrical field is constant. What if the electrical field is not constant? What would happen? So let's say you had something weird looking like this. Let's say here, something like that. 2xy I hat plus 3zy squared j hat plus 8xy k hat. Okay? So now, which component of the electrical field will yield the flux? Well, just because it's a variable electric field doesn't mean the other components will have flux now. They still won't give you a flux because they glide along the surface. It's just that they're variable, right? Only the z component will give you a flux. So the flux is going to be 8xy dA, and then that's it. The k hat disappeared. So the only difference is now I have an extra xy, right? So what's my dA? Well, in this case, since the electric field is changing as a function of x and as a function of y, I can't choose a whole rectangle as my dA, because along that rectangle, the electrical field is not uniform. It changes as a function of y, right? The higher up I go, the electric field is stronger. So what I have to do is I have to do a little square, and then my dA will become dx dy. And then I could do a double integral, right? Double integral 8xy dx dy. So which one should I do first? Well, I know y is equal to x squared, so I could do it like this. 8x y dy dx, and then integrate the y dy first, right? So integrate y dy, right? And then y goes from 0 to x squared. So integrate that part of the double integral. So the flux is going to be integral 8x. The integral of this is going to be y squared over 2 from 0 to x squared dx. Okay? So then what's that going to be? Y squared over 2. So now x squared placed in here gives you what? 8x. And x squared squared is x to the power, what is that? X squared squared, x to the power of 4. 0 gives you just 0, and then over 2. And then now you have dx. You see? So we had to resort to double integral. Now, if this one was 8x and there was no y, right? Then I could have chosen a vertical rectangle, because along the vertical rectangle, if there was no y, it has a certain x value. So along that, the electric field is uniform. So I could have chosen my dA as y dx, right? Or I could have still done it as a double integral. You can always do double integral. So you're always safe with double integral. If it was 8y, I could either do double integral, or I could use a horizontal rectangle as my dA, because along that rectangle, the electric field is uniform. You see, it doesn't change. It has the same y value, so that it's uniform. And then, so what would my dA be then? dA will be the length of this is from here to here is x, so it'll be 2 minus x dy. You see, so the difference here, this region, 2 minus x dy. Or I could still do, again, double integral. So what's my answer going to be here? This one cancels 4. So my flux is going to be 4 integral x to the 5th dx, 0 to 2, 4 x to the 6th over 6. Okay? So it has x to the 6 over 6, and then you have here, this is going to give you 2/3, 2 to the power 6. Okay? 128 divided by 3. 42. 3 goes into 8 twice. 2 left over, 6, 7 newtons per coulomb meter squared. Okay? So that's 42 and 2/3. So you can see there a good example of doing a flux, electric flux, if the surface is some kind of weird function and the electrical field is a variable. Okay, thank you very much.